In this presentation, I will talk about OLS asymptotics. This is what happens to the properties of the OLS estimators when the sample size is large. The outline of this presentation would be to first define consistency, then compare consistency with unbiasedness, talk about the asymptotic normality, and then finish with variances and standard errors in large samples. So let's provide the definition of consistency. An estimator, beta hat j, would be consistent if it converges in probability to the population parameter beta j as the sample size n increases. So here we have an estimator, a coefficient, beta hat j, that is different from the population parameter beta j, but it converges in probability to it as the sample size increases. In other words, to put it in a mathematical formula, it's the same as the probability in the limit of the coefficient or the estimator beta hat j equals the population parameter when n, the sample size, goes to infinity. And this is true for any j. So for all of the independent variables, the coefficients of these variables would be converging in probability to the population parameter. Another way to express this is with the following formula. This is a complicated formula that shows that the probability P is going to 1. So this means with almost certainty, this one is the absolute value of the population of the sample coefficient. So this is beta hat j that comes from a sample with sample size n minus the population parameter. So the difference between the estimator and the population parameter can be made less than epsilon, where epsilon is any small value. So that probability goes to 1. So give me any arbitrary small value, and we can make the sample coefficient become arbitrarily close to the population parameter by just increasing the sample size. So to read this formula, that is the probability P that the estimator beta hat j obtained from a sample size n will be arbitrarily close to the population parameter beta j goes to 1 as the sample size n goes to infinity. So this is how this formula is read. So let's review assumption 4, zero conditional mean. So this was assumption 4 of the Gauss-Markov assumptions. And that assumption said that the expected value of the error term given the independent variables xj is equal to 0. So under this assumption and assumptions 1 through 4, including the zero conditional mean assumption, the OLS estimator is unbiased. In other words, the expected value of the coefficient beta hat j equals the population parameter. So this means that if we obtain many samples, the average value of this coefficient will be the population parameter. Now we will introduce assumption 4 prime, and this is that regressors are uncorrelated with the error term. In other words, we still have that the expected value of the error terms would be equal to 0. This means that the error terms sum up to 0. But now we have that the covariance of xj and u equals 0. So this assumption is weaker than assumption 4. With that assumption, we had that the expected value of u for any x, the expected value of u had to be equal to 0. So this means that the errors summed up to 0 at each value of x. Whereas here we just want these errors to sum up to 0 overall, but for each x, we just don't want there to be a relationship between the error terms and x, But for some x, the error terms may be positive, for some may be negative, as long as there is no covariance in them, such as if we have larger errors, we would have larger x. That would be a violation of this assumption. So this is, again, a weaker assumption than what we had before. So under assumptions 1 through 4 prime, then we have that the OLS estimator is consistent. In other words, probability in the limit of beta hat j, this is the estimator or the coefficient, would be equal to beta j for all of the j's from 0 to k. So in other words, as the sample size n increases, the sample coefficient beta j would be converging in probability to the population parameter. So let's talk about the consistency of the OLS estimator. This would be the proof. Suppose that we have a simple regression model, y equals beta 0 plus beta 1 x1 plus u. And what we know about it is that the coefficient beta 1 hat would be the covariance of x1 of the variable for this coefficient and y divided by the variance of x1, right? So this was uh, from the formulas and derivation of the coefficients for a simple regression model. So again, we have the coefficient being the covariance of the variable with the dependent variable divided by the variance of the independent variable. Okay, so let's go ahead and substitute the expression for this y with this expression above. And so this is what we're doing here. And then we can go ahead and open the parentheses. So covariance of x1 and beta 0 divided by the variance of x1. Then we have covariance of x1 and beta 1 x1. So right here, and then we have the covariance of x1 and u. This is this here. So let's look a little bit more carefully in this first expression. So we have a covariance of x1, and this basically is a number, a constant, beta 0. So covariance of any variable and a constant is 0. So this term falls out. The covariance of x1 and beta 1 x1, this is the same as the beta 1 times the covariance of x1 with x1 divided by the variance of x1. But if you're looking at this expression, the covariance of x1 and x1, that is exactly the same as the variance of x1. So this whole term would be equal to 1. And then finally, we're rewriting this term and we're rewriting it again. So now we have that the coefficient would be equal to the population parameter plus this expression, which has the covariance of x1 and u divided by the variance of x1. So under assumption 4 prime, we assume that the covariance of x1 and u would be equal to 0. So if this covariance is equal to 0, this means that probability in the limit of this coefficient beta 1 hat would be exactly beta 1. So in other words, the OLS estimator is consistent under assumptions 1 through 4 prime. So let's compare consistency and unbiasedness. So here's the property. Unbiasedness and consistency, these are the desirable properties of the estimators. This is what we want the estimators to be. The undesirable property, the opposite of that would be biasness. So, and then the undesirable property for consistency would be inconsistency. So the formula is the expected value of beta hat j equals beta j. So basically, the expected value of the coefficient is exactly the population parameter, whereas here we have the probability of the limit of beta hat j equals beta j. So actually here the coefficient reaches the population parameter only in probability as the sample size increases. But in small sample, it is not. It's not the expected value of the coefficient equals the parameters. So we use the weaker assumption 1 through 4 prime. Here we use the 1 through 4 assumptions. This unbiasedness assumption is valid in any sample, small or any sample size, whereas this one is only valid in large sample. And the distribution that we would be using here, that's the t or the normal. Here we would just have asymptotically normal distribution. So the OLS estimator may be biased in small samples under the assumptions 1 through 4 prime. So the stronger, we would need the stronger assumption 4 of the zero conditional mean to get the OLS estimator to be unbiased. So again, unbiasedness is ideal. It holds at any sample size. But if we cannot achieve it with small sample, then at least we can think that consistency can be achieved in a large sample. So let's review omitted variable bias that we talked about previously. So the true population regression model is this. So if we have two independent variables, x1 and x2 included in the model, and this is the model that we need to estimate. But what if instead we estimate a misspecified model here, where x2 is the omitted variable from this model? So as you see, there's no x2 in this model. So even though x2 is not in the model, we will see it showing up in the model. And this is because if x1 and x2 are correlated, there will be a relationship between them. So let's say x2 would be related to x1 using this, this equation. Okay, so if we substitute this equation here in the equation above, so basically substitute x2 here, so that's what we get. So right here, instead of x2, I have written this expression above. And then we can open the parentheses and collect the coefficients together. So this is the coefficient on x1. So here, what we have is that the coefficient that will be estimated on x1 is no longer just beta 1. So it will be biased because this part here would be the bias for the coefficient. That's what it would make it different than beta 1. So we would have unbiased coefficient when the expected value of beta 1 hat equals beta 1. But this coefficient is biased because, again, this is equal to beta 1 plus beta 2 times delta 1, whereas beta 2 times delta 1 is the bias. So now, when would we have this coefficient not being biased? Well, there are two cases. One of them, beta 2, would be equal to 0. So if we look at the original equation, this means that x2 would not belong in the model. That means that x2 would be irrelevant. And in other cases, that when delta 1 is equal to 0. And that would be to say that there's no relationship between x2 and x1. So in other words, x2 and x1 are not correlated. So if we have omitted variable x2, and that variable is irrelevant, so its coefficient beta 2 equals 0, or is uncorrelated with the other variable, so delta 1 equals 0, there will be no omitted variable bias. So thinking about the asymptotic analog to omitted variable bias, what happens in large samples? So we have a consistent coefficient is when probability in the limit of beta 1 hat equals beta 1. But this coefficient is inconsistent because the probability limit of beta 1 hat would be equal to beta 1 plus this expression where this again is the bias. And so when would we get a consistent coefficient? Well, when again, it's the same case. When beta 2 equals to 0, so the variable does not belong in the model, or beta 1 or delta 1 equals to 0, which means that x2 and x1 are uncorrelated. So again, we would have a consistent coefficient when x2 is irrelevant or it's uncorrelated with x1. So next, let's talk about asymptotic normality. To review what we already know, under the assumption 1 through 6, these are the Gauss-Markov assumptions. In the sixth assumption of normality, we have that the coefficients have normal sampling distributions. So beta hat j, this means distributed as normal distribution, centered around beta j, which is the population parameter, and with the variance of beta j hat. So now what we can have is that under assumption 1 through 5, only the Gauss Markov assumptions. So if we don't include the assumption of normality as it's here above, the coefficients will have asymptotically normal sampling distributions. So in other words, beta hat j would be asymptotically, that's what this A means here, asymptotically distributed normally with a mean of beta j and variance of the variance of the beta hat j. So in other words, even without normality of the error assumption, assumption 6, the asymptotic normality would be achieved in large samples. So that means that even if the normality assumption fails in small samples, if we increase the sample size to become a large sample size, we can use all of the tests as if we have the normal distribution. So this normality assumption does not always hold in practice. So we saw an example where the dependent variable is not normal. The distribution does not look normal and it fails the normality tests. So in small samples, we need this normality assumption 6 for the t-tests and f-tests to be valid. But in large samples, without the normality assumption 6, we have that the OLS estimators will be normal and the t-tests and f-tests will be valid. So notice that we still need the assumptions 1 through 5 for that. So let's summarize. What are the OLS properties? OLS properties that hold for any sample would be expected values and unbiasedness under assumptions 1 through 4. These were again quickly linearity in parameters, random sample, no perfect collinearity, and zero conditional mean. Then we had the variance formulas under assumptions 1 through 5. So these are all the first 4 assumptions plus the homoscedasticity assumptions. Then we had the Gauss-Markov theorem, or BLUE, so the best linear unbiased estimators under assumptions 1 through 5. And we had the exact sampling distributions, which means we were able to use the t-tests and the f-tests under the assumptions 1 through 6, which are the Gauss-Markov assumptions plus normality. Now, OLS properties that only hold in large samples, so that's what we mean by asymptotic, so they're not valid in small samples, is that we have consistency under assumptions 1 through 4 prime, and this is that the regressors are correlated with the error term. This means that we may have bias in small samples, but in large samples we can achieve consistency, which means we can approach the true parameters with large samples. And then we have the asymptotic normality, or the t-tests and the f-tests under the assumptions 1 through 5. So let's review the variances of OLS estimators and think about what happens with them with large samples. So recall the variance of the OLS estimator, variance of beta hat j, is this expression. So here we have sigma hat squared. So this is the variance of the residual. Then here we have SSTJ. SSTJ is the total sampling variation of variable j. And 1 minus r squared j. So r squared j is the r squared of a regression of xj on all of the other independent variables. So because this is the total variation for the x variable, that is the same as n times the variance of xj. And the reason for that is that the total sampling variation is basically a summation of each of the variable xij minus the average x bar j squared. Well, that's almost the formula for variance, so that's equal to actually the n times the variance. So I just substituted this expression in here. And so let's just think about what this expression converges to. So this sigma squared j converges to sigma squared in large samples. So this r squared j, that's an r squared from a regression. So even if we have a large sample, that would settle in on a fixed number, somewhere between 0 and 1. So the variance of xj would also converge to a number. And so now we have the only thing when sample size grows is n. So it means that the variance of beta hat j would be growing at this rate 1 divided by n. Or in other words, if we take the square root, the standard error of beta hat j would be changing by 1, the square root of 1 divided by n. So again, variance is changes by 1 divided by n, and the standard error is the square root of that 1 divided by n. So this is the 1 divided by n here. So as we grow the sample size, actually the variance and the standard errors of our estimators are going to go down. So let me give you an example. Here we have the regression model of wage on education, experience, and tenure. And what we're going to do is estimate the regression model with full sample and half sample, just to see what happens with the standard errors and with the sample size. Again, that's by no means a large sample, but just to show you how they compare. And we would notice, once we estimate this model, we would notice the standard errors for the coefficient on experience and the sample sizes. So again, as the sample size n increases, the standard errors would change at the rate of 1 divided by n. And with large sample size, the standard errors would be lower, leading to more significance of the coefficients. So here are the models estimated. So wage again is the dependent variable, education, tenure, and experience independent variables. And these are the estimated coefficients with the full sample and then with the half sample. Okay, so let's notice for the coefficient on experience, the standard error in the first model is this one. And the standard error in the second model is this one. And I'm also noticing the sample sizes of 526, and I said we just picked half the sample, which is 262. So let's calculate the ratios of the standard error for the first and the second model. And so that would be 0.62. And then we can calculate the expression of square root of n2 divided by n1, and that's 0.71. So these ratios are almost the same. And so in other words, we have that as the sample size doubles from here to here, so here we're going from half the sample to the full sample, what we see is that the standard errors would actually be lower by 62%. So this is again what happens with large sample. So in general, the standard errors go down, and in general, the significance goes up, though that's not the case here. Okay, so these are the review questions to think about. First, defining consistency, comparing consistency and unbiasedness, define asymptotic normality, and think about at what rate does the sample size change when uh, the variance changes when the sample size changes. Thanks for watching.